Okay, let's get started. So today, as I said last time, we are switching tracks from sort of proofs for Markov processes to sort of to autoencoders, GANs, and so on. So I'm going to again not focus on the neural network architectures at all. I'm going to talk about formulations and why it makes sense. So this is about I'll sort of drift towards mathematical foundations as opposed to sort of network architectures. But also I'll spend a lot of time talking about parameterizations. I'll explain what I mean by that when we go into this. Okay, so this is the material which I'm talking about is taken from a variety of sources. Of course, the paper by King Van Welling, but also there's a bunch, given the importance of this topic, there are like so many blogs on this. Some of the blogs I really liked were Matthew Bernstein's, the Chris Ormandy's blog, Colin Raphael's were very informative, Yufan Jiang, Augustus Crisciari, and so on. Okay, these I've put the reference in the links. They give you more details than even what is there I have, but yeah. And for the GANs, Goodfellow et al.'s paper and Nozin and others is what I'm drawing on along with these blogs. So so this class is going to be somewhat different from previous ones in the sense of much less proofs and more sort of the setting and why these things, how at least one way of thinking about these kinds of problems. So setup is the following. So we are trying to learn a distribution. What do I mean by that? You're given samples x1 through xn from some ground truth distribution, xi's are in RD, and p star of x is the ground truth. So in terms of notational switch from last time, we always were using superstar for much of the time. Now this star has moved to sub because we'll use superstar for Fenchel dual, Legendre-Fenchel dual. So I don't want that notation to get mixed up. So I'm going to use sub here. Okay. So what we want to do is to learn a good approximation to P star. Now, there are two ways to think about this. Okay. So the first is, well, I have a class of distributions capital Q parameterized by theta. Whatever your model architecture is, and theta is in some class. And you want to learn the best Q theta to approximate P star. And you could either, so one thing could be to optimize the maximum likelihood, which is there a bit of an echo here maybe? Let me just see. Okay, one is to do ML, which means you want to find a theta to maximize log Q theta, the density. Or you could try to learn the score, which is the gradient of it. We have sort of seen scores in, in when we did Langevin, we could try to learn the score itself. So that would be the first step. And once you have this first step done, you could use this learned distribution along with some of the sampling algorithms you have studied so far, either Metropolis Hastings, Langevin, or some other SDE to generate new samples. So the goal here would be to generate new samples from this distribution. So you've gotten a bunch of existing samples x1 through xn. And this two-stage pipeline is one way to do this. Okay, and we'll study this sort of at some point during this class, these kinds of approaches. But there's also another approach, which is to directly learn a sampler without explicitly learning the distribution. Okay, so the black box will not know p theta star. The black box somehow encodes it, and the output of this box is a sample from this distribution. Okay, so you don't have explicit access to the function itself. So that's the style which I'm going to think about today. So, meaning this is just in one sense you can just think of this as a transformation. I have Z, which is a sample from some distribution which is easy to sample. Typically, we'll take a Gaussian, okay, and some function H. It's parameters by theta star, and the output is simply H theta star of Z. This is one way of thinking. Another way of thinking about it, which means that so if you find theta star appropriately such that this function transforms a Gaussian to the density of interest. Okay. That's yet another extreme, right? One extreme is actually learn the density function and sample from it. Just try to learn a transformation which goes from whatever easy random variable you know how to generate, transform it to that you want. Or you could do things, in the language of optimal transport, this is called push forward. So you take a density function, you take a measure, a Gaussian, and find a transportation map to push it forward to something else. This could be implemented in one step, in multi-step, and all these kinds of things. Okay. Or you can be somewhere in between. And that's sort of what we are going to be talking about today in terms of variational inference and the autoencoder. So the VAE pipeline we are going to study is the following. You have here, what you have access is samples from some ground truth distribution. Okay. You want to take a sample, and the first is the encoder, which moves it to something called a latent space. So Z is the latent, this is the random variable in the latent space. So the encoder is a transformation parameterized by phi. Okay. It's Q of Z given X, so the output given X. So this is this transformation. The other transformation is parameterized by theta. This is called the decoder. It takes as input Z and spits out an X from P theta of X, and ideally this and this are close. Okay. Is the pipeline clear? So there are multiple design questions here. Okay. First, what is this? What is the encoder? Second, what is the latent distribution you want? That's still open. I'm just talking about this pipeline. And three, this side of things, the decoder. What is that function you're using? So, well, so what you would do is, okay, there is this pipeline which you construct. But then when you want to generate, if you want to use this, there are multiple uses of it. From the sampling perspective, you just use this side of it. If you have trained such a pipeline, then all you would do is to sample from this underlying random variable, feed this into this box, and get a sample. This box may be deterministic or stochastic. We'll talk about that in a second. But nevertheless, this side is not of interest from the sampling perspective. This side is of interest only to build this whole pipeline so that you can get a good this and this. Okay? That's a sampling story. The idea is I want to generate new samples from P star of X. That's the sampling problem. I have given you X1 through Xn. I want you to give me new samples from the same distribution. That's the sampling problem. There are other reasons why you would use this VAE. I'll talk about it in a second. But from this perspective, so from this perspective, the first part, the encoder, is useful only in order to train a good decoder. Okay? Because all I have access to is what is being input to the encoder. Okay? So I need to design an encoder. I need to design the latent distribution and a decoder as a pipeline, presumably so that P theta of X on one end and P star of X are close. Okay? And if you do that, then if your latent distribution R of Z is an easy distribution to sample independently of this pipeline, during operation, you would just throw away the encoder. You would just sample from R of Z using some other external method, and then feed that sample into that conditional P theta, which will give you a sample X. Okay? So that is one pipeline. Yeah, there are other uses of this as well. Sujay? I'll get to good. I didn't tell you what Q is, okay, yet. What are the variational autoencoders? I'll get to a VAE. I'm being super high level right now. Before I'll get to your answer maybe in 5 minutes if you don't mind. Okay. The second use of this is sort of compression. Okay. You can think of Z as some compressed version of X. And maybe in this space, you can do your algorithms of dealing within X space can deal with it in Z space. And then once I've sort of done whatever transformations I want in this Z space, can push it back to the X space. Okay, so this, for example, in a diffusion model, this pipeline would be used as finding a good latent space. So a VAE can be used in two ways, and actually we'll see the diffusion model uses VAE in both ways, different VAEs. Okay, so there are two separate things, and we will see when we are designing the variation autoencoder how these things come together. Okay, so the design choices are encoder, decoder, phi and theta, and the distribution in the middle. Now, an autoencoder is a deterministic transformation. We are not. This is a sampler. And what do I mean by that? So let's get into, so there's an intermediate random variable in the middle. It is not what we are going to, the first encoder is going to be a transformation so that you lead to a random variable in the middle. Okay? And I'll make that more specific in a second. And this is going to be useful for generation. If you have a deterministic and deterministic, then it's not clear how to actually run this as a sampler. Okay? If Z is just some compressed version of X, and then you uncompress it, then it's not clear what exactly how exactly you'd use this as a sampler.
So you have a Q5 network, you have a P theta network. Okay. The way it's trained is you take an X, right? You makes it a Z, which is 100, like let's say X is a big event.
Z is a compressed version of X.
We get back out 1 megapixel. And you took an MLC between the 2 megapixel image, right? And just train end to end and put some regularizer on Z, like maybe the square non-regularizer, right? Or something like that, right? And then minimize the reconstruction.
Excellent.
And then after that, the way you use it is you just sample Z from a Gaussian and you run the P theta, and that's how you do sampling. And you can do simple autoencoder and sampling that way.
That is a VAE.
The L-swing norms, yes.
Yeah.
So
there's no difference between VAE.
There is. An autoencoder is deterministic. If you have stochastic inside. So what do I mean by that? In the Z space, this one, what is general? How is this implemented? Okay, you're sort of going quite a bit further, but it's many pages further. Okay, it's like several pages further, but in summary, this is what this box is doing. What this transformation is doing is to generate a mean and a covariance. And what this Z is you generate an independent sample during training. I mean, not well. This is what the encoder is. The encoder is this pipeline. So what you're generating is a Z.
Yeah.
Or actually, even during inference, actually, you're going to do the same thing. That's even more further downstream is the elbow. So I need to jump way further down. So I wasn't even planning to talk about what an autoencoder is in this thing. So I don't have anything written about autoencoders. So I'm going to start from just a VAE because I want a sampler. Okay. So so let's just get back to just the VAE. So as I said, we need to jointly train two models, the phi and theta. Okay, so the details will come in what my loss function is going to be, but that's going to happen quite a bit downstream. Okay, and we want to choose what this latent distribution is. Furthermore, you would like Z, if you would like Z to be in a lower dimensional space, so they get a compressed latent. Okay. That's another thing you'd like, not because of the sampling perspective, but because the other use of this VAE is a compression perspective. And R is chosen to be an easily samplable distribution, say Gaussian. So what we are doing is to trade off between two competing objectives. First, generation of new samples, meaning if you, I'm just rehashing what we said before, which is you sample during operation, you sample a z from R, then condition on z, we could either further sample an x tilde from p theta star of dot given z. So theta star is whatever you have trained. We'll talk about the training losses in some time. Okay. Theta star is what you have trained, and this comes from the VAE loss, which is the elbow loss. Okay. As an example, suppose this is the way you're parameterizing the decoder network. P theta x given z could be parameterized as a Gaussian with a mean with a fixed variance. So this is just a hyperparameter, and this is a learned function. Okay. In this case, how would this operation work? Well, you would first sample a z. Okay, that sample of a z would be used to get this mean, and then you would resample from this distribution. Okay, this is one way you could do the decoder. But you could another choice could be directly just a function itself. So there's no new noise, which is the decoder could be just some function of z. That's it. Okay, this is a deterministic thing. All this is allowed. I mean, these are all your design choices on what you'd like to do. In stable diffusion, for example, it's just a deterministic function. Okay? But you could do other things as well in this setting. And the choice of the decoding architecture will, of course, limit the types of resulting p theta star you can model. You may not be even possible to have the ground truth, the KL divergence, for example, between p star, the ground truth distribution, and the trained one to be equal to 0, even with an infinite sample setting. Okay. Simply, these architectures are going to what you decide, how you parameterize this is going to sort of allow certain things and not allow certain other things. Okay, this is one side of the thing. The other is the compression. Okay. So you want to transform X to a much lower dimensional space, sample from that lower dimensional space, the Z for the decoder. So, of course, through this process, you may lose some fidelity in this process. Okay? That's the other side of this game. And so just to give you some numbers, so the VAE used in stable diffusion, the X space are images. They're 512 by 512. There are three colors, R, G, and B. The latent space is 64 cross 64 cross 8. So the mu is 4. It's 4 plus 4 for the mean and the variance side of the channels. Okay. Okay. So let's get to the encoder. So this is a popular explicit parameterization of the encoder. So you take any X, the encoder generates Z by first generating a mu of X and sigma of X. These have trainable parameters. So the encoder is spitting out a pair of things. You have an independent Gaussian, and so Z is just mu of X plus diag. So you just assume that it's independent across coordinates. So it's just diag sigma of X. So there's no cross terms, and times this, just this epsilon, which is in the m dimension. Okay, that's the Gaussian. And so in words, the Q is basically Gaussian with mu and me. So this phi is parameterized to this mean and min. Okay, so this is the encoder side of it, and so this kind of a reparameterization is important because you have a random variable in it, and if you want to do end-to-end training, you need to do this kind of reparameterization because finally, otherwise you can't pass gradients through all the way. Okay. The epsilon is off the pipeline, off the pipe of the back when you push things through when you're doing the loss. Yes.
What is the explicit form of the sigma X?
That is your neural. So if you're using a neural network, is whatever your architecture is. I'm not. Maybe that's not your question. What do you mean by explicit form?
What is mean?
Is a mean. So it is the mean vector of the Gaussian. It's the mean vector of the conditional. So it's a conditional mean. So you're parameterizing Q phi Z given X as this form. You're parameterizing it as this conditional distribution is parameterized as a Gaussian with mean mu phi of X. So that's the conditioning on. And the covariance It's just a diagonal covariance with the diagonal terms being sigma phi of x. So this is an m length vector. This is an m length vector.
So you are replacing this as your estimate of the from the data, like the mean estimate from the data, and the
No, this is not the mean. This is not in the. This is in the z space, not in the x space anymore. Let's go back here. The mean estimate of the data is here. This is the mean estimate of z, the conditional mean of z given x. If I give you x, then how do you generate a z? So the way you generate the z is the density of let's say I finished training phi star, then the density of z given x is equal to a Gaussian with mean mu. So x may or may not be Gaussian. I'm not saying anything about x. Mean phi star of x, comma the covariance phi star of x, where this is simply a diag matrix. Okay, that's all I'm trying to say. Yes.
So for the inference thing, we don't want to rely on the encoder part, right? We'd like to sample from C, but what do we get from the
Let me finish the whole pipeline and I'll come back. I'm just describing various pieces of this pipeline first, and then I'll talk about it. And we'll see what the end-to-end loss function is and how things work. Yes.
This is again regarding the autoencoder and the variational autoencoder. So regarding in the decoder architecture, you said that there could be it could be represented as a distribution or a deterministic
Yeah.
function. So if it's a deterministic function, then it's an autoencoder, and if it's
But this encoder is still stochastic, always.
okay. So then I didn't get that.
Because I'm not going to tell you the difference. Because I'm not going to talk about auto. I'm not talking about what an autoencoder is at all. I'm just going to talk about a variational autoencoder, talk about where the word variational comes from because of the loss, and then you will see what happens. Sujay said that a autoencoder is compress, expand, regularizer, and train end-to-end. So we'll see what this process is, and then we'll see that.
The simplest subset of this is given an X, you get a single Z. That's not what's happening here.
That's not what is happening.
You get a distribution of Z. And from a single X,
Precisely. So an autoencoder is a compressor. This is not a compressor. This is a distribution. This is a conditional distribution.
like Gaussian in some
Precisely.
small.
So if I take a single X and just run the encoder a million times, you will get different samples of a Gaussian. It's because of the epsilons. Exactly. Exactly. This is what is happening here. So I put a single X, then what are you going to get? You will get a distribution function which you can sample using this process. So the mapping is to a distribution, not to a sample. I guess that's the sharpest answer I can give. Yeah, Sujay's answer is the best sense. Okay.
There is no different names for deterministic decoder and stochastic decoder.
Yeah, I think that's it between autoencoder and variational autoencoder. I think that's the difference.
Yes.
But yeah, for now, it's a distribution.
Can you just say a deterministic encoder is just compression?
Yes.
Yeah.
If there was no resampling, there's just compression and then an autoencoder compresses and then it expands back. Such you create this bottleneck so that you maintain fidelity. This one is generating a conditional latent, a mixture of distributions. For every X, you get a Gaussian, and what you have here is a mixture of Gaussian distribution, or an infinite mixture of Gaussian, depending on what P star is. Okay. Yes.
So the latent distribution R of C can be written as Q of Z given X times P star of X.
Correct.
Okay. So then the
Integral.
yeah, it's right integral. Yeah. So then the idea of this is to learn for the encoder is to learn a P star such that it matches the latent distribution. Right? So you're trying to learn Q of P star of Z given X. Like you're trying to learn the P star.
But what do you mean by learn a latent? I choose whatever I want. Typically, R is going to be circular Gaussian. In fact, almost the only case you want R to be something easy to sample, so just circular Gaussian.
Okay, it says
Yes.
and target P star will not.
Yeah. In fact, you will not get it. Let's continue. There is going to be a trade-off, and you will see what. Let me just sort of go down this road, and then we'll come back and talk about this. Okay. So first, all I want to at this point convey is what the encoder is doing. Hopefully that part is clear. Okay. Then next piece. So how is this? Now we'll get to actually the training loss of the VAE. Okay. So there is a phi that parameterizes the encoder distribution and theta that parameterizes the decoder distribution. So let's start with the maximum likelihood problem. So I want to find a theta star that maximizes log p theta of x. Okay. This is your standard. I want, right? If I'm giving a bunch of samples, find a model that best fits the distribution. This is an objective function. Instead of directly learning this, let's expand this problem. Let's consider that now I've agreed that the z I want is R. That's the distribution I want for z. So let's look at this joint space of x comma z. Then, if I have this joint space of x comma z with the marginal of x being theta, p star, the marginal of z being R, the log p theta can be written as just the marginalizing out of z of the p joint of theta and, of x and z. Agreed? So we can write this as I can multiply and divide by q phi of z given x. Okay. So then in which case I can bring these two together and think of this as an expectation. So remember, x is a fixed, x is given here. Okay, so it's not random. So I can think of this, what I've circled in red, as a function of z, and this is an averaging with respect to that some particular distribution. So this is nothing but the log expected value of this ratio of p theta x comma capital Z divided by q phi of capital Z given x. So the theta and phi are the things which we are trying to learn. Okay. Now we can do Jensen's on it. So this is where variational thing comes in, and swap the expectation of the log. Okay. And so you get this thing, which is, so a Jensen's lower bound on log p theta of x is nothing but, well, is the average over z sampled from the conditionals of q phi of dot given x. Okay. Remember, q phi is the first step, the encoder step. Okay. Of log of the joint of x and z divided by q phi of z given x. So in this case, this is just a black box function. Okay. So think of this as the function of x, and then you're just applying it to this random variable z, and you're averaging that. Is it clear so far? I haven't done anything fancy. So we'll split this up in many ways. Okay. But one way of splitting it up is just write it as, this log, I can write as log of numerator plus log of 1 by denominator, which will give you this. But we'll split it up in other ways in just a second. Okay. So let's go back to the elbow. Remember this function, this is what is called the elbow, that function of x. It's actually parameterized by two things, theta and phi. It's log of p theta by q phi, average with respect to q phi. So what's p theta of the joint of x and z? It's the conditional of p theta x given z times r of z. Okay? Because the joint, you can just write it as this. This is exactly what you said a few minutes back, which is why I sort of punted the question to this point. Now we'll start working things out, and you'll see what exactly the loss is. Okay. In which case, now you can write this as the following. You can write it as this alone, one integral, okay, which is nothing but the average of, this is the expected value of log p theta, the average, the conditioning with being taken with respect to z down here. So x is fixed, z is the random variable. So it's a weird thing here, okay? And you're sampling z from this distribution. So this is the first term, okay? And I will argue that this is about the fidelity of generation. The second term is, so we have already taken care of this. The second term is log of this ratio. It's q log r by q, which can be written as q negative of q log q by r, which means nothing but the KL divergence of q and r. Good so far? We'll argue that this is essentially a compression term. So is the algebra clear? We'll start. The thing that's weird here is the random variable is sort of in the conditioning term of this, because we are just treating this as just a function right now. Okay. Okay. So let's look at the first term. Claim that this is about the fidelity of generation. Let's see why. If I were giving you, so p theta is some density function. And remember, x is a fixed sample. If I was giving you any flexibility on p theta, I could shape that function however I want. How would I shape it? I would like to shape it because the density function, and I want to make this as this function I want to maximize. If I want to make this as big as possible, then I want to make this as big as possible, which means I want x and z to be aligned, because the delta, right? When z equal to x, p theta it simply copies this data, and so latent is simply a copy of a data, and that's what will maximize this function. Does it make sense, or not really? So remember, I'm now thinking about this from the perspective of phi and theta. Okay, let me just repeat once more what I said. I'm just looking at this from, so I've fixed an x. This is now just a function of phi and theta, and I want to see what would be the properties of phi and theta which will make this as big as possible. The claim is that simply copying x is what, if there was no dimensional collapse, if m equal to d, simply copying x would maximize this function. Okay.
The reward for the z is its likelihood of generating it, right?
Yes.
So you want q phi to generate high reward z.
Correct. You want q phi to generate high reward z's, and you want to make p theta such that it is actually a high reward.
No, the reward is defined by its likelihood of generating it.
Okay.
Right? So like that's my reading.
But there's a p theta as well. I can shape the reward function as well and the generator. I can shape both theta and phi. That's what I was trying to get to, that subtlety. Okay. So you need to sort of talk about how both need to adapt, and the argument is they both are aligned together when it's a copy, or not just a copy, any permutation. Suppose x had a finite level of values and z is any permutation of that, they will all, there's not a unique optimizer, but this is an optimizer for this thing. Okay. Okay, that's what looking at this as a function of phi and theta tells us. Okay, so which is why this term is thought of as fidelity of generation. Okay. The other term, let's see what the other term is doing. This is a compression term, meaning this is a Gaussian. This is always the same Gaussian. There's no x in it. This is a function of x. Okay, this is what we are trying to optimize, this phi. So it's trying to make if you want to make this as small as possible because of the negative sign, you want to make every q phi of dot given x. You want phi such that for any x, they're all the same. That's what makes the second term as small as possible. And you want to make it as small as possible because there's a negative sign in front of the KL. Does it make sense? And so the second term is trying to push it's trying to push all the conditional distributions close to each other. Okay, so this is the compression term. Okay, so now you see how this even sort of the thinking is somewhat different from the autoencoder. The reason is, I think the cleanest answer is what Sujay said, is you should think of it as optimizing conditional distributions. That's what you're trying to do in the middle space. Okay, so you want to see what are the right conditional distributions you want so that you can get both fidelity and compression. So let's do a specific calculation. Okay, so suppose that the p theta is a sampling decoder. Okay, what do I mean by that? It means that you're just choosing a learnable function for the mean. It takes a z as input, but the variance is fixed. It's just just diagonal with just a scalar. Okay, so then log p theta, because this is a Gaussian, is some normalizing constant minus, so this is a function, z is given here. So x minus g of z whole square divided by 2 sigma square. That's how the log of this is there. In this case, the elbow can be written explicitly in this form. The first term just becomes the square loss difference. So this also goes back to what Jacob was saying when it's the in this. I think this is sort of what you are alluding to, maybe. Yeah. But the optimization here is still with respect to, okay, so let's go back to the fidelity statement again. I think in this place, it becomes even more explicit. So you've got this kind of a parameterization. So if I only cared about the fidelity, which is this term, then what would you do? Well, g theta of z, z should just copy x. That's what is the right thing to do to maximize this. Okay, so you don't want every conditional distribution should map x to each as a separate thing. Of course, the space, there's no compression at all at this point because x and z are essentially identical to each other. Jacob.
How am I going to get rid of this? Is that the trick where you bring it inside? If I'm sampling z from Q5, how do I?
Yes, I haven't told you how. So there are issues. We'll get to that. I'm just first writing the loss function, and then we need to worry about how to reparameterize this so that we can actually take gradients. Okay, that's another issue. So we'll come back to that in a minute. Okay.
The dumb the classic autoencoder, not variation. What it involves is, instead of this expectation, we just put g5 right into z, right? So your expectation of x minus p theta of z, or whatever the g theta of z, right? But instead, just put the q5 also in there, right? And then that's the loss function. So just remove the expectation.
Right, you're saying that I'm not doing a distributional, I'm not trying to optimize the conditional distribution function. You're basically having just a compressor and decompressor such that end-to-end is met, and you want this to be as small as possible.
This will be a different loss function.
Yeah.
Once you tell us how you do this expectation.
Correct. And already you can see maybe one thing. What is Q phi? It's parameterized by the mu and variance, which means this expectation is the same as the expectation with respect to a standard Gaussian. But when z is written, because any Gaussian can be written, if z is a Gaussian with certain mean and variance, it also can be written as mean plus standard Gaussian times some matrix. So once you put it in, then you can do the gradients through this. That's the reparameterization trick. That's all. I'm going to write that in a second. So we will just write the z as mu plus epsilon times sigma. And once you write it that way, the expectation is now with respect to just a standard Gaussian. There's no phi anywhere here. And so when I want to do gradients with respect to phi or theta, then everything is clean because it's inside the loss function. Okay, so that's why I sort of brought that reparameterization right up front. Is it making sense what I'm saying? Yes. Absolutely. So let's go back to this. So this is a parameterization choice. So there are two things that are happening. There are some probabilistic rules going on, but there are also some parameterizations going on. So just to keep them separate, I'm putting a delta on top of this to say that this is how I'm going to, I have chosen to build my function, which is transforming from z to x in this manner. This is a design choice. Once you have done that, then you can start, then you can do chain rule and all on this object. But I have decided that this is where this object is going to be. And actually, we'll come and revisit this thing again and again. So this is what in the beginning of the class, I said, I'm going to focus on parameterizations. So when you're trying to build a VAE for sort of a discrete diffusion model or a discrete language model, then what is the right parameterization? Okay. So that's where you have to spend a lot of, you have to think about what's a good parameterization so you get an interesting architecture. There are two parts to when you're sort of building any of these kinds of things. One is how do you parameterize whatever your functions are? And two, what is the actual neural network or transformer or whatever architecture to actually instantiate this parameterization? I'm not going to talk at all about the second one. I'm only going to talk about what structures are reasonable, and then within these things, how you build each one of them is a separate problem. Does it make sense? Okay. Okay. So this example also, I realized when I was talking about the L1 and L2 loss, things were not very clear why it collapses. Hopefully here it's much more clear why copying, this is all about fidelity. Because the function, if you want to choose phi and theta such that any x transforms to the same x, that will basically make this as large as possible, okay? Which is about fidelity. Yes. I'll come to that later. I talked very quickly in response to an answer, but I've written it out in a few steps. Just next slide. Okay. And this side is more clear that because this side depends on x and this does not depend on x, if I want to optimize this, then it should phi should be such that for any x, it should look like R, which means it's getting q phi is such that q phi of dot given x1 should be close to q phi of dot given x2. So this is that's why this is a sort of compressing term. Okay. Does it make sense, that part? Okay. All right. So now coming to the reparameterization. Okay. So if you are given n IID samples, then this is what you now, given what we talked about, the VAE training objective is to maximize the elbow of xi, where xi is sampled from p star. Okay. So you need to take gradients with respect to phi and theta. And so the gradient with respect to phi is tricky, as you pointed out, because it's a conditional, it's an expectation with respect to a distribution which is parameterized by phi. But this is where this reparameterization helps. You can write z sample from q phi as, because of the encoder architecture, you can rewrite because this is just a conditional Gaussian. You can write this conditional Gaussian as mean plus diag, because we said that there's no covariance, that they're independent across coordinates. It's just the variance per component or standard deviation here, times standard Gaussian. So you can rewrite this way, which means that you can take this particular loss function and replace this by expected value over epsilon. Okay, let's write that actually here. You can write this as expected value z in Gaussian, not z, sorry, epsilon, of x minus g theta of mu phi of x plus epsilon sigma phi of x. I guess there's a diag, it's a matrix, so I should do the diag of that, norm square by 2 sigma decode square. Okay. And so that now, once you write it this way, phi and theta are somewhere inside the expectation, and you can do chain rule and all whatever else you want. Okay. It's just compositions of functions. Good. Does it make sense now? What I meant by reparameterization? Okay. So if you do that, let us say mu theta is some function h1 phi, log of sigma phi is h2 phi. Then there are explicit forms for all this. We can write, the other part is there's a KL. The KL has an explicit form. The first one you can simplify it further and write it in a form where you can actually start doing gradients on it. Okay. So see this blog post too for actually an exact derivation. Let's go back for a second. Now that we have talked through it, let's just summarize various pieces. We want to find an encoder such that you get a distribution out here, a conditional distribution over here. What you have then, this one's marginal, is the mixture of these conditional distributions. And the goal is to make this mixture of conditional distributions as close to a Gaussian as possible, the mixed distribution. That's going to be the compression term. But you also want to have each conditional distribution such that you have fidelity, meaning when you take this conditional distribution and then go back to the other side, you want to have end-to-end. You don't want to lose the sample quality. So this is really the trade-off we were looking for. But we did something, this is the motivation, but we did something here, which is a Jensen. We switched a log and an expectation. Okay? So we started with log maximum likelihood, but what we are doing is unclear the connection between maximum likelihood and this, simply because of, from the maximum likelihood perspective, because we have actually used a Jensen and switched it. This has an intuition of its own, which is what we discussed so far. But it has drifted away from how close to the ML it is. Okay. So can we fix this problem somehow? Okay. So essentially, at a high level, the VAE will use the elbow with the Jensens, and we want to now somehow control what is going on, how much we are losing there.
The decoder adds up that C, right? It is actually induced by the input of mean x and variance of x. But while doing the sampling, I may not have that.
Correct. While sampling, you will not have that. So you will just pick a standard Z. So if you want to, okay, just as a mental model, suppose that your distribution was 2 modes or something like that, okay? What this pipeline while training would have done is to take some part of, you have a standard circular Gaussian state space. Some part of it would be called mode 1. Some part would be mapped to mode 2. Okay, so when you're running when you're generating new samples, you just need to generate enough from these 2 modes corresponding to P star. So what happens? When you draw a sample of Z, sometimes it's going to be on one side, sometimes on the other side. And G theta has learned to sort of map that side to one particular mode and the other side to some other mode. Does that explanation make sense? Okay. So you're partitioning the Gaussian state space in some manner, okay, such that each one corresponds to many modes if it's discrete. But if it's continuous, think of the continuous analog of that. Okay. So yeah, during inference, and if this whole pipeline has worked perfectly, then you're going to generate new samples from whatever P star was that. But you could do other things as well. And when we come to sort of diffusion models, latent diffusion models, we will use VAEs in 2 ways. One, to find a Z, which is a compressed version of X. And 2, in that latent space, we will use another VAE, quote unquote, to actually generate samples in that latent VAE space. Okay? You could, right? It depends what you want to do there. Okay, so it's but you have so you could use VAEs in multiple ways, for example. Okay. Okay, so now let's switch from VAEs to GANs. Okay, so the goal is we want to control this Jensen gap in some manner. Okay, let us see whether we can do this kind of a thing by also sort of being maximum likelihood in some sense or closer to that. But before I do that, I want to talk about some intuition on the KL divergence. Okay, so I want to talk about the forward and the reverse KL divergences. So what I mean by the forward KL divergence is the following. Suppose P star is a ground truth distribution and Q theta is some parametric family of distributions that your model will generate. Okay, and theta, where theta is a learnable parameter. Then what is KL of P star Q? It's nothing but integral of P star log P star by Q. That's the KL. Okay. So let's write this as P star log Q star minus P star log Q. Okay. This is this has the interpretation of sample x from P star and compute the expectation log P star of x. That's this first one. Okay. There's no theta anywhere in this one. The second one is P star log Q theta. So minimizing KL between P star and Q theta. Since this has no dependence on that, is the same as maximize over theta log Q theta from x and P star. Okay? These two are equivalent. Note that in this case, there is no P star anywhere in this functionally. P star only appears here. Since there's an expectation, I can approximate it with samples. I'll just draw n samples from P star. And so I can approximate this by maximize over theta, 1 over n log Q theta hexagon, which is nothing but maximum likelihood estimation. Okay? So forward KL is the same as maximum likelihood estimation, maximum likelihood cost function. Is it making sense? Okay. So what is the problem with this? The problem with this is the following. Let's say that my function class is somewhat underparameterized, the theta function class. Okay. Let's say it's just a unimodal Gaussian of standard variance. Let's say I can just pick the mean, the trivialest problem in one dimension. Okay. So Q theta, basically, all the theta allows me to do is on a line, put the mean point. But other than that, it's a Gaussian. But P star is a bimodal distribution. Then Q, the function class I'm optimizing over, is just Gaussians with parameter theta and variance 1. Okay, scalar. So therefore, KL P theta and Q, P star and Q is of this form. We have just this. So let's make the following observations. Suppose Q theta is small in some region. Okay, so it's far away in the tail of the Gaussian. Then log P star by Q will be large because Q is the denominator. And if it happens that when Q theta is small, P star is large, then you're in trouble because this is putting a large cast. In that place, there's a density P star, which is weighting it up. And this is really small, so this ratio is large, so this whole thing is large. Okay? And remember, you want to minimize the KL, which is maximum. There's a negative sign, so you want to make this as small as possible. You want to minimize the KL because P star and Q theta should be close to each other. That's what you want. Okay. So if your theta was chosen such that it was small when P star was large, then it's a bad, from this cost function, such a theta is bad. Does it make sense? Okay. On the other hand, if Q theta has a very high probability over regions where P star is small, it doesn't matter. Because P star is small, the integral doesn't, as long as P star is small, it doesn't matter what Q theta is doing. Okay. So this divergence, a forward divergence, will push to this kind of a solution. It will basically make sure that over high probability regions of P star, okay, the two peaks of the mode, you want to have as much of Q star as possible. Okay, even if the penalty is that over low probability regions of P star, Q theta star is large. Because in this place anyway, because P star is small, this doesn't matter. It'll just null it out because the cost function doesn't care because it's only average with respect to this measure. Does this make sense? So, which means forward KL looks for multimodal sampling, but may generate lots of atypical samples. Okay, what I mean by atypical samples is it actually generates samples where there's nulls actually in this multimodal thing. Okay, now let's go to reverse KL. Okay, let's look at Q theta and P star. So all we have done from corresponding to the previous one is flip these two. So it's Q log Q by P. So let's see what happens here. Now, if Q is high over regions where P star, okay, now let's look at it. Here's P star. Wherever P star is low, this thing is large. So Q needs to make sure it nulls out those places. Okay, because this is my design choice now. So what does this mean? That means that you want solutions of this type. Okay, you want alignment of whenever wherever P star is small, you want to make sure that Q is small. Wherever P star is high, I don't care. I mean, the reward, if I miss a P star which is high, it doesn't matter because the Q is anyway wiping it out. So in this mode, I don't put any mass, it doesn't matter. I just need to make sure that I align my Q star with at least one mode and make sure that other places I don't care about it. So a reverse KL leads to mode collapse, okay? Meaning you will sample from like one mode, okay? Typically, and if you look at it, you should go to the biggest mode because that's where you'll get the most mass, most value, okay? It'll lead to mode collapse, but it will not result in too many atypical samples, okay? So this is forward versus KL is the intuition. Okay. Now, this was just a digression. Now let's get back to so what you'd like to do is maybe reverse KL because you want good samples, or you want some combination of these kinds of things. Okay, we'll see how we address that as well as address sort of the Jensen gap. Now, that's what the GAN is doing. Yes. Yes. It depends. I said I gave you the intuition from the underparameterized case. Okay. There's a second issue. When we go through the GAN solution, the other side, you will see why this kind of solution is bad in scaling. Okay. So there are two issues. How do you scale these kinds of things? The first one is straight gradient descent to train it. What we are going to talk about now will involve a min-max optimization. It's much hairier to actually run at scale. Okay. So I'll come back and talk about, I can expand on that once I've talked about the second piece as well. Okay, so in fact, beyond just forward and reverse KL, you could try to combine these two. I want some forward and some reverse, right? I could use some combination of these kinds of things. So in general, let's, for example, something like a Jensen's Shannon, which is a symmetrized forward and reverse. So you could try all these kinds of things. So, but first I want to get to what is the problem with reverse KL. Suppose you don't care about mode collapse. Okay, I say that I'm willing to pay the price of mode collapse. It's still very hard to implement reverse KL. The reason is the following. Okay. Let's write the reverse KL expression. Okay. KL Q P star is Q log Q by P. This I can approximate by samples, but samples of what? Samples, now this expectation is not with respect to the ground truth distribution. It's with respect to the samples of the distribution that is learned. Okay, it's a different distribution. Problem number one. Bigger problem. I don't even know P star explicitly. I don't functionally know what P star is. Okay, and this cannot be approximated by samples. Forward KL is very clean because the P star in this, there's P star log P star by Q. Okay, so the first part P star log P star I don't need to worry about because it has nothing to do with my optimization. So I just need to worry about P star log 1 by Q. And that's really nice because I can approximate the P star by samples. It only appears to the integral. The cost function is always fixed. Okay, so I can actually run standard gradient descent and deal with it. Here, I don't know how to actually even implement this because P star I need functional form. I cannot approximate this by samples, and I don't have the functional form. Okay, that's a huge problem with the reverse scale. Okay. So there are various issues we have brought up. How do we address these? Okay. So let's look at optimizations of the following form. Okay. Suppose that I want to minimize some F divergence between P star and Q theta. This is neither forward or backwards because I haven't told you what this F divergence object is. Okay. So F is some convex function. Suppose I choose F is U log U. So the F divergence is defined as Q times F of P by Q. That's how we are going to define the F divergence. Okay. That's this. So if I put F is U log U, then this thing becomes the forward KL. Okay. You can check the algebra. By just substituting F is U log U in this thing, df P star Q becomes KL of P star and Q. If you put F equal to negative log U, then it becomes the reverse KL. These things switch actually here with this function. If you put F is root of U minus 1 whole square, this becomes something called the squared Hellinger divergence. Okay, some other metric. And the reason the last one, if I put it as this function minus U plus 1 log U plus 1 by 2, this one becomes the average of the forward and the reverse scales. Okay, so some symmetrized thing. This is the Jensen-Shannon. Okay, so you can start thinking about mode. You can use this thing to have a whole bunch of things between this trade-off of mode collapse, atypicality, and so on. But we haven't addressed, so these divergences are useful in that sense. But we still haven't addressed the core problem. I don't functionally know P star. I only have samples from P star. Okay. So how do we address that? So let's revisit in your convex optimization, Legendre function duality. So if F is a convex function, then the convex dual F star is supremum of ut minus F of u. You have seen this in many other classes, including when you have done mirror descent or in your probability class when you saw the rate function and the log MGF. You have seen this duality in different settings. I've just redefined it, that's all. So this is the Fenchel transform. And so in this convex setting, then if I take F star and stick it in, Tu minus F star, so the supremum over all T gives me F of X again. Okay? They're duals of each other under some nice conditions. So now let's do duality to F divergences. So let's look at the F divergence of P star and Q. Remember, by choosing F, I can make this a forward KL, reverse KL, whatever else I want. Okay? All of them are in this form. This is Q times F of P star by Q. I'll write the dual form. This can be written as the supremum over T times this is the argument U minus F star of T. Okay? I've just written the definition of the Fenchel dual. Note here that this optimization is inside X, inside the integral. That means this is really T of X. I'm trying to choose a function here. Okay, right? That's what the T is. Because for every value of X, there's a different value of T. Okay? So let tau T script be the set of collections of functions sufficiently rich. Okay, if you want to see more about this, you can look at this paper by Nguyen and Wainwright in IT. The reference is there. So this is some rich enough class of functions. Well, first, then this thing can be lower bounded in the following. The supremum can come outside the integral, because of which you get a greater than or equal to. Remember, this T is some function of X, so we'll call it T of X. I'll supremize over all functions T in this class. P star, so if I look at this, Q and Q cancel. It's T of X, P star of X, minus look at this part, it is q star, f star of t is a t of x. Okay, I've just done that. Okay. But this integral is just nothing but the expected value of x with p star. This integral is nothing but the expected value for some other random variable y, which is sampled from q theta. Is this good? Okay. And in fact, under reasonable condition, there's a closed form expression for t star, which is nothing but f derivative of p star by q theta. Okay. So the summary at this point, if you just to catch back, I wanted to find I wanted to q theta was some family. I want to minimize over parameters theta the f divergence between p star and q theta. So various problems we have looked at fit into this framework. And we have, and if you look at because f is convex, under reasonable conditions, we can show that this minimum is exact. This is, we just showed greater than or equal to, but this is tight, okay? And it's tight with this t star. So which means we can write this minimum over theta as the minimum over theta, maximum over all functions in that class t, okay, whatever that function class we were using, of expected value of t under p star minus expected value of t under q theta. We can write as this difference. So remember here, we need to optimize a t for inside each one. Let's stack all that together, but this inside an integral, so it's actually t of x. So we are actually optimizing a function here. I'll stack, t star is the stitching together of all of that, is that function. Okay, so which is what is happening here. So t is a function. So the lower bound is p star times t of x. This t is t of x. Okay, this q theta and q theta cancels, and that's why you get p star times t of x. And this soup has gone outside, remember, the lower bound. So I get q theta times f star of t, which is a function of x, which is t of x. Okay, so this is an expectation with respect to p star of this function. This is an expectation of f star, which is known, because that was in your design choice. For example, it was minus log u or u log u or one of those kinds of things. So you know what f star is. And t is basically the function class. Does it make sense? Correct. Your design choice. So if you wanted to do standard reverse scale, f star would be u log u. Wait, let me see. What is f star? Yeah. So I gave you the f's here. What is the f star associated with it? You can write it out as well. Okay. There's a table somewhere. I didn't write the f stars, I guess. Oh, I did. Actually, I have done this. Okay. So no, I did not write the f stars. Okay. But this is the f's. You can get the f star and you can get the t star. There's a table.
Based on some like distance.
F. Okay. What is f? Is some convex function in the f divergence. Is the definition of f divergence. You choose an f, you'll get a distance between distributions, quote unquote. Okay, KL is not a distance, but yeah, but essentially that's what it is. So if you want a forward KL, you choose f is u log u, but you know that that's basically what we did when we started the VAE discussion. If you want the reverse KL, you'd use f is minus f of u equal to negative log u. If you want a symmetrized version, then you'd use a Jensen-Shannon, which is this function. And then in that optimization problem is f star. You can there's some expression for f star as well from this. Okay, so what we have here is we have said minimizing the f divergence can be written as this min-max problem. Are you fine so far with writing it this way? But look at this problem now. We don't now need to know p star anymore. Okay, this is done from samples of p star. This is done from samples of q theta. okay, this expectation. But you have an optimization over functions in the middle. Okay, so how would you actually solve this problem? Is that you could do some so it's a min-max optimization. You could do there's alternating gradient updates. All sorts of things can be done here. But it's not clean like just standard gradient descent. You need to do something else because there's a t. You need first of all a batch of samples of theta, okay, for each fixed theta. Then you need to adapt your theta. Then for each theta you need to solve for the t, and then go back and forth. Okay, there are people in this room who know far more about min-max optimization than I do, but this is the formulation. How you solve it? Is it reasonable? How does it scale? That's a completely different story. So now coming back to sort of things at very large scale, empirically, min-max optimizations are very, very unstable. Okay, so these kinds of methods are good up to some scale, but at the bigger scale, things are going back to sort of elbow and just parameterize it large enough. The model essentially. Okay. So you have seen today what a VAE is, and even though I hadn't planned, what an autoencoder is, as well as what a GAN is. Not the architecture, but where they fit in this story. So you see that in the GAN, just to complete what I started with, there was a Jensen gap. There isn't anymore because we made it a min-max problem. You pushed it to that. But so that's one way to address that gap of what we did with the VAE, but you're paying a price in this business.
When you said that the function class must be sufficiently large, that means it has to contain the T star.
It has to, yeah, exactly. It has to contain this function, essentially. Let's go back here. Yeah. This function should be somewhere in the class. Okay. So, but just because it also contains, it's not clear how to solve that problem. Okay. Because solving that, how do you alternating grade? You need to do some alternating gradient updates. Will it converge? When will it converge? All sorts of other things come up in that rule. But that's how do you sort of solve that problem? And the next question I didn't even address is what's a good architecture so that you can solve it. None of that had been addressed. I just told you what these model classes are and where they sort of fit together. That's all I've said. Okay. So what I want to do next is, now that we have seen this VAE, I want to come to diffusion next class. We are going to do it in two ways. In the next class, we'll look at it as purely a flow thing. In the class after that, we are going to reconsider the diffusion and just see it as purely a VAE, a multi-stage VAE. It's not just a latent Z. Here you saw one latent. Imagine if you had a VAE with latent Z1, Z2, Z3, Z4 up to Zn, and then a decoder. Okay, then what does it mean? So we'll see a diffusion as simply a multi-stage latent model. We'll see both these views, and both are actually very useful. Sort of when you're sort of, in one view, you will see why sort of something from MMSC gives you denoising models. Then in the other view, you will see why you get denoising starting from sort of an elbow and a VA view. So that's what the next two classes are going to be. Okay, thank you very much.